Um, Welcome to this new chapter. So we're going to be covering continuous probability distributions. We have already seen the discrete probability distributions. Remember we said with a discrete probability distribution, the variable of interest will assume very specific values. And you can normally enumerate all these values by using things like counting rules, like combinations that we have seen with the hypergeometric and the binomial distributions, and even the uniform distributions. But when it comes to what you call a continuous probability distribution, the variable of interest can take on any value, and it basically is not possible for you to actually enumerate all the values that the probability distribution can take on. And in these situations, usually will apply to most natural, when you're measuring most natural phenomena like time, weight, height, and so on and so forth. So I'm going to start off with what you call the uniform probability distribution, which is very similar to its a discrete counterpart. But the difference is that when you're doing a uniform continuous distribution, like I said, the variable of interest may assume any value with the same probability, but it does not ever assume a specific value. So it takes on any value within a range of values, any interval within a range of values. If you've got equal intervals within a range of values, then you basically have the same probability that the value lies within that interval, but it never actually assumes a specific value. For instance, before with the binomial and hypergeometric distributions, we could calculate, for instance, the probability that we have a certain number of successes. But for continuous distribution, you're going to be looking at the probability that the x lies between a certain a and a certain b, certain limits. So we normally do speak of what you call a probability density function if you're dealing with a continuous probability distribution. And when you plot this on a graph, you're going to take the area between 2 points. You're going to take the area between 2 points, between the two limits. And it's for a uniform distribution, for instance, this is going to be described by this step function. So basically you have some f of x, and the density is going to be some uniform value, which is 1 minus b, 1 over b minus a, where these b and a are basically the limits. If you look at an example, you could consider, for instance, a situation where you have an aeroplane and you have some historical data, and you know that the flight time is always between 120 to 140 minutes. So in this case, you have a plane going from Chicago to New York. So x can assume any value between this 120 to 140 minutes. So these are the lower and upper limit. So the lower and upper limit, basically this is what you have over here. The a is the lower limit and the b is the upper limit. So in this situation, you have computed the arrival times to the nearest minute. So you're going to have 1 over b minus a. So that is 1 over 140 minus 120. So which is 1 over 20. That's what you have over here. Actually, you should reverse this. So that so just a minute. So we should really have the definition before the actual equation. So yeah, so you have something like this. So this is the upper limit. So in this case, our upper limit is basically 140 minus 120. So this would basically describe uniform probability distribution. And when you plot it on the on a graph for uniform probability distribution, you're going to have a rectangular distribution, and the height is essentially this probability, which is uniform, hence the name. So this is uniform for all. It's basically the same probability for every single for every single section of the graph. And overall, the probability density, the total probability density is going to be 1 necessarily, because probability relates to sum to 1. And the expected value is going to be this is the formula for expected value, which is a plus b over 2, and the formula for the um, for the variance. So I want to go into how you actually do derive this formula, but it stems from integral calculus. So it's basically you integrate over the squared deviations, and you'll come up with this formula. So you could just memorize this. Works for me. So for instance, we have an example here. Well, we could have done this for the plain example, but we have an exercise, a small exercise that we could do over here. So we have a uniform probability distribution, uniformly distributed between 1.0, between 1 and 1.5. So you want to see to show the graph of the probability density function. So it will basically be something of the sort where this limit over here is going to be 1, and then this other limit over here is going to be 1.5, and then everything for the height. So the height of the graph, if you want to see the height of the graph, is going to be so the height of the graph is going to be 1.5. So it's basically 1.5 minus so the inverse of that, so 1 divided by 0.5 is basically the height of the graph, because you know the overall probability, which is basically the height of the graph times its entire length, which is 0.5, it has to be 1, right? So that's going to be the height of the graph. So you have some graph from 1 to 1.5 with a height of with a height of 2. Then you want to see, should a graph probability density function. So a probability density function is going to be so you have some so it's basically f of x is equal to you need a one-sided bracket, so you need one of those. That's what's happening. It's hanging. Maybe open it again. So probability density function, you're going to need to insert that equation. Start a new equation. You have some f of so our f of x is equal to you need a one-sided bracket. Just a minute. So you have one of those. Then you have isn't this working? Okay, let me try one more time to do this without, let me see. So you have some f of x equals 1 over 0.5. So it is 1 over 1 over 0.5 for x. So this is for 1 less than or equal to x. Less than or equal to x less than or equal to 1.5. And then you have the second, and it is 0 elsewhere, right? So you have this this is your step function. Then let's see, what else do we have? We want to compute the probability that x is is equal to 1.5. So this is really easy. The probability is 0. We said that the probability that it assumes a specific value is actually 0, because that means, remember, we are using integral calculus. So if you actually collapse the probability to any specific value, it means that the area under the graph, at a specific point, it means you have no interval. So the interval is 0, meaning the area is actually 0, and the probability is actually going to be 0. So this actually comes from integral calculus. Then the probability that you're between 1 to 1.5, 1.25. So this is basically quite easy. So you already know the height of the graph. The height of the graph is 1 divided by 0.5, which is 2. But then you want to have, let me see, and the width of the graph between 1.25 and 1 is 0.25. So those are the limits. You have 0.25 by 2. You get a 0.5. So this is going to be a probability of 0.5. So you want to see then the probability that is between 1.5. So how can we do this? We can get the nearest value. So let's take maybe that the probability is less than. So we could rewrite this maybe, because I need a less than or equal to, right? So this could be, maybe let's do 2 decimal points. It's going to be that probability less than or equal to x, less than or equal to 1.5, 1.49. What's the difference between the two limits? So 1.49 minus 1.19, you have a 0.3. So that you can compute by the height of the graph. The height of the graph was 2, so that's a 0.6. So this should give you 0.6. It should give you 0.6.